This is Professor Rogers. This presentation discusses Pearson's R. Pearson's R is used when both the independent and dependent variables are numeric. The statistic is named after famous English statistician Carl Pearson and is known by many other names, including Pearson's product moment coefficient and the correlation statistic. It is referred to using the symbol little r. Always use little r, not capital R, which stands for something else. In terms of the key elements of an inferential statistic, Pearson's R has direction, magnitude, and statistical significance. The example in this presentation comes from a state-level dataset. 4 variables are used: the log of the violent crime rate, the log of population density, percent urban, and temperature. Note that 2 of the variables are logged. Pearson's R works best when the variables are normally distributed. The variables in this example have been checked for skewness, and the transformed variable is included when appropriate. In SPSS, the output is obtained using the path Analyse Descriptive Statistics Bivariate. In PSPP, the path is more simple: Analyse Bivariate Correlation. Here is the command dialog box. The variable list for the dataset is on the left, and the variables are toggled into the box on the right. The default settings are used in this analysis. The resulting output is shown here. This output is from SPSS. Similar output is generated by PSPP. The box that I highlighted shows the association between the log of the violent crime rate and the log of population density. Violent crime rate is the row variable, population density is the column variable. Here are the 3 numbers in the highlighted cell made larger. We will interpret everything here. The first number is Pearson's R. The sign is the direction. Since the sign is positive, we conclude that the association is positive. In other words, as the log of population density increases, the log of the violent crime rate also increases. Pearson's R is a standardized coefficient ranging from -1 to +1. The magnitude of the relationship is the number without the sign, and we use the interpretation for standardized magnitudes mentioned in the video titled An Introduction to Inferential Statistics. Here Pearson's R indicates a moderate relationship. Thus we have a moderate positive relationship between the log of population density and the log of the violent crime rate. Statistical significance is shown twice on this output. The number 0.032 is the p-value. Keep in mind that with statistical significance we are testing the null hypothesis. In a moment we will see that the formula for Pearson's R includes the mean and the standard deviation, so we know from the theory of sampling that the underlying numbers reflect a range of values, not a single value. A 95% confidence interval can be built around the coefficient of 0.032. The null hypothesis is that R equals 0. The p-value of 0.032 is less than 0.05, which means the 0 falls outside the 95% confidence interval, and therefore we reject the null hypothesis. The asterisk next to the Pearson's coefficient of 0.301 also conveys the p-value. The asterisk method is available only in SPSS. A footnote on the table tells us the meaning of the coefficient. 1 asterisk means that the p-value is less than 0.05, and 2 asterisks mean that the coefficient is less than 0.01. The asterisk system is a common way to report statistical significance. The final number, 51, is the n. Let's look at the underlying math to understand how the statistic is constructed. Here is the formula for R. The numerator is called the covariance. It is the distance of each point of the x variable from its mean multiplied by the distance of each point of the y variable from its mean. The sum is not based on squares, so the numerator can be positive or negative. If both the x and y distances are positive at the same time, the relationship is moved in a positive direction. If they are both negative, the negatives cancel each other out, and the movement is still in a positive direction. If one is positive and one is negative, then the relationship is moved in a negative direction. The denominator is the standard deviation of x multiplied by the standard deviation of y. The use of the standard deviations in the denominator has the effect of standardizing the coefficient. Notice that values on one side of the table are the same as on the other side of the table. For example, the correlation between the log of the violent crime rate and the log of population density is the same as the correlation between the log of population density and the log of the violent crime rate. This feature is called symmetry. It does not matter which of the two variables we designate as independent and dependent, we will get the same result. Later in the video series, we encounter statistics not having symmetry. The correlation of a variable with itself is a perfect positive correlation having a value of 1. On this matrix, these perfect correlations fall along the diagonal. Here the results are summarized in an APA table. Note that only half the table is reported. We don't need the other half of the matrix because of symmetry, and we don't need the diagonal because this information is redundant. Notice that the asterisk system is used here to report statistical significance. The footnote contains the interpretation of the asterisks. This footnote should be included even though the convention is well known. Only one variable, the correlation between temperature and percent urban, is not statistically significant. In this presentation, we learned about Pearson's R. Pearson's R is used when the independent and dependent variable are both numeric. The coefficient is a standardized one with a value ranging between -1 if the correlation is perfectly negative to +1 if the correlation is perfectly positive. If there is no relationship, the correlation is 0. Its elements include direction, magnitude, and statistical significance.